to module 5, and this is our last module for the day. So we may be able to finish early, or if we have time, we can continue to move forward. But this is where we can spend some more time as well. So estimating motor parameter. This is critical when you want to get the maximum out of your motor, okay? Now, what you see in the market today is you can buy an off-the-shelf inverter and you can actually tune your inverter to run your motor. But the problem with that is you can never really get maximum torque and efficiency out of that arrangement, okay? Because in order to get maximum torque and efficiency power out of the motor, your tuning has to be for all the operating regions, all the operating conditions of the motor, right? So this is a critical chapter to understand how to get really the most efficient inverter motor combination for your end application. So we're going to have certain assumptions. We're going to talk about modeling of the motors and estimating actual motor parameters, and then we'll have an example here. All right. So we are going to assume here that stator windings produce sinusoidal EMF. So we're not talking about trapezoidal waveforms. We're not talking about space harmonics. We're talking about, very sinusoidal EMF for the sake of estimating motor parameters. Now, space harmonics and air gaps are neglected. Now, we talked about all those air gaps and all those discontinuities in the air gap. So we're going to ignore that there are discontinuities so that we don't have any non-sinusoidal components in our analysis. We're going to say air gap reluctance have a constant and sinusoidally varying component. So let's develop the math. With these assumptions, we can assume further that you have balanced three-phase supply voltage, and we're going to neglect for the time being eddy currents and hysteresis effects at the moment, okay? And we are going to also state that stator reference axis for phase A is chosen in the direction of maximum magnetomotive force when a positive phase A current is maximum. You'll see that what I mean in a minute, all right? Stator self-inductances are maximum when rotor Q-axis is aligned with a particular phase. Okay, this is where now we talk about how the Q-axis needs to be aligned, all right? Mutual inductances are maximum when rotor Q-axis is midway between two phases, all right? So I'm going to give you examples of all of these statements one by one so we can understand, okay? So here is your motor, okay? And we're going to say we have an A phase where you have, this is your A phase winding in the motor, okay? You've got a current going in and current coming out, or this is going in, that's coming out. Okay, it's going in, coming out, right? This is an arrow coming back, this is an arrow going in. Okay, so this is going in, coming out. Then we have a B phase at 120 degrees. Then you have a C phase at 120, okay? And we are going to have this alignment of this phase, A phase. A phase is middle of A winding. Okay, that's your A phase, middle of A winding. And we are going to have now a theta. Okay, this is very different than before. As I said, before we align the theta with the D axis, now we're going to align the theta with the Q axis. Okay, now we align the theta with the Q axis, the math changes because the projections change. So when you align the theta with the Q axis, now this is your actual motor. If you can see here, this is our rotor in the middle, and this is my north magnet, this is my south magnet, and I am picking the middle of the north magnet as a D axis, and then I'm picking my A axis to be the center of the A winding. Okay, these are important constructs to understand so that we can simplify our math. Now, we are going to talk about we're going to talk about your self-inductance, or actually this should be the inductance of phase A. What are the components of inductance of phase A? And we're going to talk about the inductances of phase B, phase C, and then we're going to talk about inductance of AB, BC, CA. So what we are saying is the inductance of phase A consists of three components. First component we say is the self-inductance. Second component we say the leakage inductance. And third component is because of the interaction with the magnet. Okay, we call it Lx, and it has got cos 2 theta. And I'll explain to you what cos 2 theta is. Right? We are saying here 2 theta is a term introduced due to saliency. Right? What is saliency? So we'll discuss saliency in a minute. Right? Similarly, B axis you add 120 degree, C you subtract 120 degrees. And then your AB, all the components you have is minus half of LS0 plus LX 2 theta minus 120. And BC is, so you basically have, so if you compare with your, say, inductance, so you have a mutual inductance, which is, so you're assuming that your self-inductance is all equal, LS0 for all three phases because they have the same number of turns and they're geometrically identical. So AB is essentially what you're sharing between A and B phase. BC is what is being shared between B and C phase. And then C is what's being shared between C and A phase. All right. So the terms come out to be, you have the magnet interaction as well between when you have the mutual inductance between AB, BC, and CA. So here we say when Q axis is aligned with the particular phase, self-inductance is maximum. Okay. So when the Q axis is aligned, theta value here is going to be 0. And therefore, this value will become maximum. Okay. When Q axis is midway between phases, mutual inductance is maximum. That means this values will be maximum for the mutual inductance. Okay. Now what you have to realize is as the motor moves in the magnetic domain, its inductance is going to go up and down. Okay. The maximum value is LQ and the minimum value is LD, right? So let's look at that further. So this is your inductance for phase A is plus Lx when you're aligned with the Q axis, and it is minus Lx when you are at 90 degrees. So this basically essentially points you to, and we're going to combine all these inductances into LD-LQ. All these LA, LB, etc., and mutual inductances, we combine all of them together into simply LD-LQ so we can handle the math much more easily. Now, what is saliency? So surface mount, and I'm going to explain to you through flux lines, surface mounted permanent magnet motors are non-salient. And what does that mean? Okay, let's observe what that means. So I have some flux lines to show. So we'll come back to this and explain to you what non-salient means and what saliency means. Now here, going to, again, this is your back EMF term, and your essentially, you can say LDI by dt plus EMF term here. So if you take per phase equation, your RSIA plus your LDI by dt plus your EMF, that's what this means. Okay. So these are for phase A, B, C, individual terms. Then if you take the flux linkage now, see this is where the flux linkage comes in, the concept of flux linkage. We are taking all these inductance terms, and now we're trying to simplify the math. Okay, so we have this concept of flux linkage where we say, okay, lambda A consists of all these terms, including the magnet. Lambda B consists of all these terms, including the magnet. Lambda C include all these terms, including the magnet. Okay, and we go further to simplify lambda MA as having one lambda M, which is constant, and then its dependence on the rotation. So we simplify these further. So here we come back to our math. When we have theta with respect to Q, the math comes out to be this, where we have dq transformation happening from ABC, right? And then you can have anti-Park transformation, ABC, happening from dq. Okay, so you have essentially Park transformations, anti-Park transformations, again, going back to how theta is correlated with respect to the a-axis. And here is your simplification, where now we boil down to VQ, VD axis, where you have RS IQ plus the term P lambda Q plus omega lambda D. So here is your change of flux, right? So change of flux in lambda Q and change of flux in lambda in D axis, right? And here you have VD is equal to RS ID plus P lambda D minus omega lambda Q. And the question is, why do you have negative in the VD term? So VQ, so when we have ID equal to 0, essentially this term drops out, and you have only these two terms remaining. Okay, so still your controller, although you're going to have ID equal to 0, your controller still has to generate some amount of voltage VD. Okay, VQ has to account for back EMF component, which is incorporated here as lambda omega lambda D. Now the negative term here is essentially, if you look at the back EMF term in terms of DQ, you're going to have a negative component of the back EMF that has to be accounted for in VD. So your controller indirectly compensates for back EMF in the D axis, which is generated from the Q axis, and that comes out as a negative component. Does that make sense? All right. So hopefully it is clear. If not, feel free to send me a question so I can address it by email as well. All right. So here is your flux linkage in the Q axis, which is now resolved to flux linkage, resolved to the inductance in the Q axis and the current in the Q axis. And your flux linkage in the D axis is sum of your inductance in the D axis times ID plus lambda M. Now you have to, if this is 0, then this flux linkage is simply equal to the magnet flux linkage. All right. So the statement is synchronous inductances are effective inductances seen by phase winding during balanced operation. Okay. So, all right. So let's boil it down. LQ is equal to 3/2 LS0 plus LX plus LS1. And LD is equal to 3/2 LS0 minus LX plus LS1, right? So this is your average value of the inductance. This is your position-dependent component, and this is your lead, right? So that's your simplification. And we go further here. Let's see. I think we have already discussed that equation. This is a more elaborate explanation how you actually code it when you're trying to do simulation. I'm going to show you a PSPICE simulation, which we do using these equations. And all right. So here is your power input equation based on DQ axis. Here is your power output equation based on DQ axis. And you have a torque equation, which is essentially function of magnet flux and IQ. And then you have got this part, which is a reluctance torque. And this, in case of a non-salient motor, this is going to be 0. So you're going to have no reluctance torque in surface mount motors. So you only have this simple equation. Okay. So here is the PSPICE simulation, which we're going to get into shortly. And I'll come back to this. And let me just, before we go into it, what I want to do is talk about, again, some flux lines so you guys can kind of see what's happening inside the motor. Okay. So here, you can see here that these are the magnets. Here we've got a north magnet and south magnet. We have a phase A center line between, this is your A winding, this is your C winding, and this is your B winding. Okay. And what we're going to do is we're going to see what's happening to the flux lines. So here is your D axis. Okay, basically this is you're at 0 position. 0 current and 0 rotor position that's our position, 0 rotor position. Now, so what you see, I want you to pay attention what's happening inside the motor, right? So your lines of flux are going around, emanating from the magnets and coming back, right? So these are closed loop lines of flux. And what you would see is what is your flux linkage along the d-axis and what is your flux linkage along the q-axis. Now this is, remember, this is without any current in the winding. So what you would see is your flux linkage along the d-axis is actually zero, right? There is no flux linkage. So you imagine d-axis being a plane. There is no flux crossing the d-axis. As a result, d-axis flux is zero. Flux linkage is zero. Whereas you have some lines here crossing the q-axis, right? So you have some flux linkage in the q-axis, right? Now this is called saliency when your d-axis and q-axis fluxes are different. Now, let's see for another example of this one. So this is when we rotate 90 degrees, right? 90-degree position of the rotor, what happens? Again, at 90-degree position, we get some flux linkage in the d-axis. You can see some flux lines crossing this plane, okay? So we get some flux linkage in the d-axis. Still, the q-axis has got most of the flux here, right? That is called saliency when your flux linkage is different between d-axis and q-axis. And that's what leads to different LDLQ. That's what leads to reluctance torque. Let's look at that here. Now here we have actually got the round magnets, okay? And we said this is our d-axis, this is north, this is south. Again, we have got A, B, C windings. Let's see what happens. So here, what happens here is you have, this is your d-axis, and this is your q-axis. So you can see here, you have flux lines crossing here, and you have flux lines crossing here. So you can make a case here that they are potentially equal because you have the flux lines coupling both of these planes. So when you can make a case that d-axis flux linkage and q-axis flux linkage is equal, then you have saliency, known saliency, I should say, okay? And here again, you can see here is when you go to, so this was your 90-degree rotor position, okay? 0-degree rotor position is different case. In here, you have on the q-axis, zero flux linkage. Lines are parallel. So again, you imagine a plane and your lines are not intersecting this plane and all the lines are intersecting in the d-axis. So here you have a good amount of saliency. So when I go from 0 rotor position to 90-degree rotor position, my flux linkage essentially on the d-axis remains about the same. Okay? Here's another example where your magnet coverage is not 180 degrees, right? They are curved magnets, but they are not covering the whole 180 degrees. So see what happens here. So here again, you see the d-axis, you have at 0 rotor position, you have no flux linkage, and q-axis, q hogs all of the flux here, okay? And similarly here, you go to 90-degree rotor position, you can see here that you have some flux linkage in the d-axis, and you have a lot of flux linkage here in the q-axis, all right? So here is a summary of what happens. So here you have surface mount permanent magnet motor, where you have full coverage, 180-degree magnet span. Then you have surface mount with a 90-degree magnet span. And then you have IPM motors, which are basically your magnets embedded inside the rotor, okay? So here you have, if you look at LD, comes out to about 0.102 millihenry. And LQ is about 0.103 millihenry, pretty close to each other, okay? And average is about 0.102 millihenry, right? And you have this flux, zero current flux, which is basically your little less than residual flux at 0.0114 Weber, okay? And you can convert the D flux and the Q flux also into Weber here. When you have a 90-degree magnet span, you can see the differences being emerging between LD and LQ. So here you can see there's a difference between the two at zero current. Okay, at zero rotor position, there's a difference. And you can see here in a lateral magnet, you have a big difference here. This is the difference we try to exploit in IPM motors to be able to use the reluctance. Okay. Now let's go back to, and I guess I'll come back to the simulation. Let's continue forward. Is everybody still able to hear me?
Yep.
Yes.
Okay. All right. Wonderful. So let me talk about, now you have got a motor for which you want to design your controller, right? And in order to design the controller for this motor, you have to characterize the motor properly. And manufacturers can give you, some guidance in terms of characterizing the motor. But if you want to exploit all of the capabilities of the motor, we want to know everything there is to know about the motor. So the first thing we want to know is the resistance of the motor. Now, the resistance of the motor is dependent upon the temperature. And you can use this equation, which is neglecting skin effect. R is given by R0 K plus T divided by K plus T0. So R0 is the resistance measured at T0. So you could say it is a room temperature resistance. And RT is a value at different temperatures. So this is the value you should have in your controller when you're trying to drive. You already perhaps know, most of the time you may not know the motor temperature. But if you know the motor temperature, then you can calibrate your controller to respond to changing resistance. Okay, so it becomes more adaptive control when you can take care of the resistance in your motor. Okay, so here is a way to measure your LD, LQ values, where if I were to short phase B and C, and I were to apply voltage here, then I can compute that my function, if I apply a sinusoidal voltage here, you can basically say 3/2 RS plus 3/2 LQ. P is basically your d by dt factor IQ. Okay, and LQ basically comes out to be 2/3 measured inductance at theta equal to 0 degrees, right? This is basically, we know that the maximum inductance is when the theta is equal to 0 degrees, when the Q axis is aligned with your center of the winding axis, right? And LD is your value is when theta is 90 degrees. So this is a way to determine LQ/LD. Now, mind you, LQ/LD values will change with current. So it's important, and normally as a controller, when you take off the shelf motor, you do not know what the value of LQ/LD is or the span of the current, right? So that's an important factor to determine for precise control of the motor. So here is what we call a current decay method, another simple method to determine what the inductance of the motor is. So you can use the same equation here. And what you can do is you can essentially turn on this switch first, build the current in the winding, okay? And then close the switch and turn this off. And you measure the decay of your current in this resistor. And when you measure the decay in this resistor, then you can essentially determine what the value of inductance is of this combination. You can lock your rotor at 0 degrees, as has been shown here, and at 90 degrees, do this test and determine your LD/LQ values, right? This is the first step in determining LD/LQ. Now, here is a more complicated method. If you have access to the neutral, then you can lock the rotor, keep the currents balanced, and measure inductance for various values of current and position. Position is simulated by different current magnitudes, right? So you have to, this is a very complicated setup. You have to have a variable resistor here. You have to make sure the currents are balanced. IA, IB, IC remains balanced. The rotor is locked. And then as you lock the rotor at different positions, you want to measure the inductance based on the current you push in the. So The simplest, of course, is this method here. This is easier to set up, and you can lock the rotor, and you can measure. You don't have to lock precisely at 0 degrees. You could lock at different positions and measure the decay value and determine your inductance, because all you have is R and L component here. You already have taken into account the resistance of the winding. So you take that into account, and then this becomes a pretty simple DC power supply equation. You can have even two MOSFETs or IGBTs doing this part, so that you can very easily measure the inductances, right? So LDLQ is critical in being able to have precise control of your motor. And then the other part is you want to also know what is your magnet flux linkage. So we define the magnet flux linkage as square root of 2 by 3 times no load voltage divided by omega, right? So omega is essentially your mechanical speed. So this is electrical speed. Omega is your omega M mechanical speed times 4 pairs, right? And you can define your back EMF constant as no load voltage divided by omega. So this is essentially your back EMF constant. So you can also determine lambda M by this equation, where you can use the torque and the current, in this case IQ, to determine your lambda M. Okay, so once you have determined lambda M, R, LD, and LQ, you are ready to control the motor. So now the other part which you have to keep in mind is that your values, LQ, LD, and lambda M, are going to change with temperature. And so what is going to happen is, as you get into higher temperatures, higher currents, you're going to have saturation taking place. And that saturation is going to confuse your controller, because you don't have the exact characterization of the motor. So in this case, this is a way to characterize the motor over your temperature and your current range. So what we're going to do is we're going to say, okay, in a linear region, we are going to say IQ is less than some value I naught. But at high currents, IQ is greater than I naught, okay? And we're going to say LQ is subjected to saturation. And LD and lambda M are subjected to armature reactions. At high currents, we are going to use what is called Frölich's formula to calculate LD, LQ, and lambda M, all right? So this is the Frölich's formula, which basically says that you can determine, and this is your LQ in a linear zone, and this is the current level where you're maintaining the linear zone, right? And so you determine the dependence of LQ with the current with this equation. And I'll give you an example here, okay? Similarly, you can determine LD, and similarly, you can determine lambda B. So you can see LD and lambda B have got this factor B, which we are going to take into account. And all of these are function of IQ, okay? So here is your results. Let's say you have 6 poles. You measure the resistance to be 1.9 ohm at 25 degrees Celsius. You have no load voltage of 106.8 volts, 1000 RPM. You have an orthogonal torque, 17.6 Newton meter at 10 amp RMS, and 31 Newton meters at 20 amps RMS. So you can already see a saturation happening, right? Your L0 value is 21.1 millihenry up to 10 amps RMS, and then it goes down to 16 point. So L0 is your LQ value. It goes down to 16.08 millihenry at 20 amp RMS. And your LD value is 12.2 millihenry, then goes to 10.73 millihenry at 20 amps, okay? So with these numbers, what I ask you to do is determine A and B. So there'll be another homework to do, is determine the values of A and B given these numbers. Okay, so this gives you the complete characterization of your motor to be able to use in your controller. Now you can actually have an adaptive control that changes based on your operating conditions and you can have much better control, much better utilization of the motor you're trying to control. Okay. So any questions so far before we dive into this short PSPICE simulation? I did go, sorry, go ahead.
This parameter estimation, like practically if we see our machine can be connected in star or delta. So even if it is delta connected, we can assume it to be star connected and then just do it. Is it? Or we have to take it separately?
That's a good question, Deepak. So when you connect the motor in delta, you are going to have, I believe you can follow the same procedure in terms of, so yes, so I think you can still assume, so you basically still have, well, I guess we don't have access to, so this will not work with respect to delta configuration in this case. This also will not work in terms of delta configuration. So I think delta configuration, and this could work in delta configuration, where you have access to all the windings at the same time. But then you...
So, sorry, for this configuration, you don't have the neutral, the access to the neutral. So how it's going to work?
Sorry, could you repeat that, Romanos?
Yes. So in this configuration, you don't have, there is no neutral in the delta configuration. So how this example is going to work?
Right. So yeah, that's a good question. So essentially, delta configuration doesn't have neutral, but you do have access to all 6 terminals, right? So I don't know, Deepak, in your case, whether you have access to all 6 terminals independently, or do you think, let me draw it, for example. Let's see here if we can draw it real quick. Let me go back to our drawing board and see if we can do this math real quick. Give me a minute while I bring the chart. All right, so when I have delta configuration, so I can say I have A dash, B dash, C dash. Is that the case, Deepak, where you have access to all 6 terminals?
Yes.
So if that is the case, then I can essentially, so I can separate this between A and A dash, and then I have B and B dash, and then I have got C and C dash, and these are linked together, so this can work, right? B and C dash, okay. So this can work in terms of, and you could put a variable resistor here, so this can possibly work to determine LDLQ values. But your LDLQ values here, what you have here is going to be different, right? So still, I think you got to figure out a way to, so effectively, you can use the same technique, but your LDLQ values compared to Y configuration obviously are going to be different. So in this case, when we have a Y configuration, so when I'm applying a voltage, I'm applying across 2 windings at the same time. Whereas in delta, I'm applying across here. So the inductance seen by a delta configuration is going to be less, correct?
Should be 1/3 in case of balanced load, means balanced winding inductance.
1/3 in case of delta or Y. So if I have, so which one will see, if I have got VD, VQ, VD, right? Which will require more voltage, Y or delta? Which will require higher VQ if you have exactly the same motor?
But delta would require more voltage, no?
That's correct, yes. Because, yes. So delta would require more voltage. But why would you use delta winding? Do you have, are you using delta winding to have better performance? I mean, obviously you can achieve, if you have delta connected winding, obviously you are applying much higher voltage to the motor, so you can have a higher speed.
Yeah, one outer rotor motor is there, which is delta connected.
Okay.
So for higher actually bus utilization.
Okay. All right. So I think it's interesting. We have finished our, so let me show you the PSPICE simulation, which is, again, it's a very simple simulation. I'll be sharing the files so you guys can actually download it and play with it. I was hoping to convert into LT-SPICE, but we didn't have a chance to convert into LT-SPICE, which is better now than the PSPICE. But you can also download the PSPICE from TI website, which is available for free nowadays. So let's go back to our PowerPoint. Okay, so in this case, I'm going to simply show you PSPICE implementation here, or maybe I'll show you in the. So this is, again, you can download this from TI's website, PSPICE. And what we have done here is, and I'm going to go to your, I've got two simulations here, but I'm going to show you. Well, let me start with this here. So what we have here is, so here what we have is, I'm going to show you the setup. So first is, here, this is the motor model. Okay, so the motor model here is, we are, essentially what we have done is, so this is VD and this is VQ. So if you look at your equations, and I may have to share this back and forth between, I apologize, this is going to be back and forth between the PowerPoint and this. So this is the equations we want to simulate, okay? You have VQ as a function of RS, LQ, IQ, omega LD, ID, omega lambda M. And then you have VD as a function of RS, LD, ID, LQ, IQ. Okay, and then you have your input power, output power, torque. So these equations, what we have coded in PSPICE. So what we have is, essentially, this is kind of an equivalent model in PMSM, of the PMSM motor. You have RS, you have LQ, you have IQ current here. This is a function of omega lambda M, and this is your function of omega LDID. And for VD axis, this is your equations, right? Now, how do you implement this in PSPICE? And so in PSPICE, what we have done is, so this is kind of shows you, you have your inductance, D, you have your resistance. Now here, what you have is, you take this VDP, which comes from here. So VDP is essentially your, VDP comes from here, which is essentially your omega LQ IQ. So if you see, you take the current flowing through this loop, which goes from here, essentially goes through this loop, and you bring that up to this VDP. You connect this here, right? It'll make sense in a minute here as you go through this. So, and then you multiply this with omega E, which is a multiplication here. And this is your H block with the LD. So this basically gives you omega ED, right? So you have this current flowing, which is your ID, current flowing through VD loop. And you have omega E multiplied by LD, which is the gain of this block. And then you have that, and then you bring over from the Q loop, bring over from the Q phase, this omega LQIQ. I think it's going to be maybe a little challenging to explain here. Let me see if I can. Best would be for me to give you guys the PSPICE simulation. You guys can see it and run it and see how this is implemented. So this gives you the motor model where you have omega LDID, omega lambda M, all these terms accounted for, so that you implement the VD loop and the VQ loop, and then you have the torque loop in the bottom, okay? And then you have, let's see here. So this is your current loop, where you have a simple KPKI current loop. Here you have a feedback for the D current. You set that to, this is your reference, you set the reference to 0. And for the Q axis, you set a reference, and you're the Q feedback, your PI. Now what you do with this is, based on your D and Q PI loop, you generate what I used to say duty cycle, okay? But this is not really a duty cycle. This is your actual VD and VQ voltages, right? You could imagine you have a two-phase inverter, and you could then take this D and Q duty cycle. That's what you would have in case of, if you were to drive a PWM waveform. is then you take this D and Q duty cycle and convert it into a DQ voltage. But in this case, we're going to take this output as a VD, VQ voltages. And that's what it means here. I eliminated the inverter section, two-phase inverter section, and say, okay, no, we can use the duty cycle to directly mean this is a VD, VQ voltages. And they go through a current sensor, which is essentially this is the current sensor. You're measuring the feedback. So this is your current going through the D loop. This is the current going through the Q loop. And you have a small filter here, 10 microfarad, 10 ohm filter. So you have feedback of the D loop and the feedback of the Q loop. Okay. And here is your motor mechanical equation where you have got torque minus your load torque. This is essentially your load torque here. Okay. The load torque is implemented here, divided by the moment of inertia. Then you integrate this to get your speed omega m. And this essentially is some kind of a load which you can simulate. It can be a fan load, an arbitrary fan load which you can simulate to put a load on your motor. Okay. So this equation here is your, and I'll draw it in a screen here so you can understand it. Let's go back to, so what you're implementing here is essentially you have this equation, torque of the motor minus load torque divided by moment of inertia, J, that, and then you integrate this, that gives you your, now we are ignoring any frictional torque, okay? We are not adding that part. For simplicity case, this is essentially what your equation is on your PSPICE module. So let me bring that back up, okay? And then you have this arbitrary, essentially, current source, which acts as a load. And you can look up how to implement this. You'll have the simulation to run it. And then let's move forward. So this is your electrical conversion. You take your mechanical speed, convert into electrical speed, electrical radian per second, and then you can simulate your torque speed characteristics here, what's happening to your torque with speed. You can look at your VD and VQ values. As you can see here, the VD is negative, which is expected, and VQ is positive, which is expected. And then you can see your ID, IQ values. You can see that IQ is positive and your ID is 0. Okay. So that is the PSPICE simulation. It's a working model, which I'm going to see if we can bring it back to the PSPICE. So this is your motor model, VDVQ. Now you can go further. There is also in this you have Andy Park and Andy Clark transformations that you can play with. And then this is your PI loops. You can play with different reference values. Here, you can do phase advance, you can do -5, and see what happens. This is now this is where you can do a two-phase inverter, where you could actually convert the value coming from the D and Q current loops into duty cycle. And you can clamp the duty cycle between 0 and let's say 97%, and then convert that into your voltages. But you don't need to do that because the output of the PI loop itself, you can directly convert into VD and VQ. And the motor model here, you can see it is a little complex how it is implemented, but you can trace it out. It's a working model, so you should be able to trace it out, how different voltages are connected together to form the voltage model. And then that is over. You can also implement speed loop on top of this, where now you can convert the output of your speed loop into a current reference, right? So without field weakening, under your base torque and speed curve, you could run this experiment. You can also play with the dynamic response of your speed and how the motor responds to your speed command. This is okay. Now here, there is more involved. So here what we do is you basically, so you've seen this. This is your torque minus the load torque, which is here. divided by the motor inertia, and integration of that gives you the speed. Okay. Now, what we have done here further in this section is we have gone ahead and generated a ramp, a position ramp, which you can use, a 0 to 360 position ramp, which you can use to, so what we do is, and this math is, I think you can find all of this math on one of my blog posts, how this is done. But essentially what you're doing is taking the speed value and converting it into a 0 to 360-degree ramp, which you can use for computing your anti-transformations. Because anti-transformations here, you need the value of the position. So that's what it does. It basically gives you the position. So I think that is what's we have here. Close this. We'll see if we can run the simulation here before we go to the next steps.